We're gone. We're good to go. Okay, before starting what we have to do today, I would like to go to a couple of problems, solve a couple of problems from the set of exercises that were available. Because today we will start another chapter. I'm going to do problem 10. So I'm doing problem 10 from page 95 of textbook. If I want to put a header on today's lecture, I would put conditional probability. So, okay, we're recording. Just want to make sure that we're recording because some time ago when I was first starting using this kind of technology, this is a more advanced tablet that I have. But still, it can do one or two things that are not authorized, that is not authorized to do. I had spent an entire class writing on the tablet and all that, and none of it was recorded. I was mad. I had to redo it again at home. And that was really, really bad. I was mad. So in problem 10, we have two different sets. And we know their probabilities. We have the probability of A being equal to 0.4, the probability of B equals 0.5, and we also have the probability of the intersection. And the problem is asking us to find first the probability of A union B. And that is automatically an application of this formula which we mentioned last time. So you have all the numbers that are needed. 0.5 plus 0.4 minus 0.3, and all this will give you 0.6. So the probability of A union B, or A or B as we call it, is 0.6. Now let's do one. What is the probability? Let's make a picture here because that will help. So here is A and here is B. And A union B is the area that I can draw with red. Essentially enclose it with red. So the red is A union B here. What is enclosed in red? Now look at the second set. A complement intersection B. So what is A complement intersection B? Which are the points that belong to A complement intersection B? Those points or those simple events in A complement intersection B, it means that X satisfies the property that defines B, but it does not satisfy the property that defines A. This is how we should interpret this. And I'm saying this because it gives us a good cue for today's lecture, because today we'll not be talking with sets in this context that you see in this particular problem, but will be much more specific. We'll give them properties, tangible properties, well-describable properties. So what is A in the A complement intersection B? How are we going pictorially to put this? We should not be inside A, but we should be inside B. So if I choose the yellow, where should I put the yellow? Here, correct? Right there. All this is the part of B that is not inside A. So this is the part of whom the probability, this is the set of whom the probability I want to compute. Now, look what I have. There is a middle part here, and I need to change the color a little bit. Let's use the purple. What is the purple part? A intersection B, very well. So if I put the purple and the yellow together, then I get the entire A, the entire B, correct? So purple plus yellow gives you B. Well, that means, and also you see that those don't have an overlap, and whatever leaks are just leaks in the color, okay? Artifactual leaks. I mean, these type of things that are marked a little bit with red. There is no overlap between the yellow and the purple. So in this, we can actually say that the purple is A intersection B, and the yellow is A prime intersection B. And if you put them together, you have A intersection B union A prime intersection B. The two give you B. And those two are exclusive events. So based on the properties of probabilities, the probability of B is going to be the sum of the probabilities of these sets, of these events. Therefore, if this is the probability that I want to find, I simply need to subtract the probability of the probability of B, the probability of A intersection B from the probability of B. And therefore, this would give me, if we use the numbers, 0.5 minus 0.3, that will give you 0.2. Correct? Now I want to do the final question. What is A prime union B prime? Everything outside of what? Outside of the union. So what is the union? The union is an OR, okay? So let's put OR here. So we say X, how should we interpret this? X in A prime or B prime, what does that mean? That A does not satisfy the property that defines A, or X does not satisfy the property that defines B, correct? Now this OR is not exclusive. It's not an either or, it's OR, plain OR. It's not exclusive OR. Therefore, if we want to go here in my little pictorial representation, where should that X be?
Everything that's not purple.
Everything that is not purple. Why is that correct?
Because the purple is A and B, and A and B is going to be.
Yeah, but you use automatically the rules, the De Morgan rules. I want essentially to derive the Morgan rule, the De Morgan rule. A prime union B prime. Not everything in the box. Everything. The correct answer is. Let me see because okay, I got rid of that. The touch screen is very sensitive, and when I'm trying to pay attention to what each one of you says, I do uncontrollable movements here. It should be everything except the purple. Why? Because if you are here, of course, you don't satisfy neither of them, okay? If you are here, X does not satisfy B. So that fits the OR description. Likewise, if X is here, it does not satisfy the property that defines A, but satisfies the property that defines B. The only position that is not allowed to be is in the purple. So A, that allows X to be everywhere but on the purple region. Okay, so this, as we say, is S, as we, actually we'll write it in terms of the De Morgan laws, and that's what it is A intersection B prime. So this is what we call De Morgan, one of De Morgan's law. The other is the dual, and the dual is A intersection A prime intersection B prime is the union, the prime of the union. That's the other law. So based on this law here that we explained actually why it works the way it works, the probability of A prime union B prime is equal to 1 minus the probability of A intersection B. Because this set is equal to A intersection B prime. And we said when you want to find the probability of the prime of a set, of the complement of a set, then you simply subtract the probability of the set from 1. That's what applies here. And that probability is 1 minus 0.2, therefore this is 0.8, if I properly recollect. No, 0.3. So that's 0.7. And that's the answer to this problem. Problem 10. Okay? Any questions? I'm not going to be giving you more stuff like that, but we're simply going to do a few more problems, to do one more problem, and then we will continue with conditional probability. Okay, let's go to the following problem that actually prompted Chevalier de Marais to ask Blaise Pascal. So we have a game of with a die, a single die with 6 sides. Now, it's not inside the book, so don't try to find it inside the book. I did it in my previous class, my 3238, but it's nice because actually it combines counting rules, simple counting rules, with sets, with the rules of probability. So you win. Here's the rule of winning. Roll a die 4 times, up to 4 times, and score a 6. So you roll it up to 4 times, but you win once you score a 6. So if you score a 6 at the first roll, then you don't need to roll 3 more times. You're a winner. Now, if you don't roll a 6 during the first roll, then you got a second chance, and a third chance, and a fourth chance. And if all 4 chances that you're given, you haven't rolled the 6, then you are called what? A loser. Yes, you lost the game, okay? So that's the rule of winning. So if W is the event win this game, what is the probability of winning? We want to calculate the probability of W. Well, let's see how W can occur. So I define the following events. W1, win with the first roll. W2, not score a 6 during the first roll. First roll, score with the second. Win, roll 6 in the second roll. We'll see. Let me. What do you think should be W3? What did I say? Not score a 6 during. Oh, that's why I couldn't fit it on this morning on the screen. Because I fit it in the previous lecture, and I said, why is it longer now? Not score a 6 during the first roll. Score a 6 with a second. No. You have up to 4 times to try. Yeah, roll a... No, it's not the sum of 6. You have 4 attempts to roll a 6. If you don't roll a 6 during all of your 4 attempts, then you lose. But if you roll a 6 in any of your 4 attempts, you don't have to continue to exhaust all of your attempts because you've already won. There's no point of rolling again, and you don't gain any more points. So what is W? What should be W3? Yeah, you roll the 6. Roll 6 on the third, but no 6 on the first 2. And finally, W4 is almost on the fourth roll, but no 6 in previous 3 rolls. Okay, now you understand that W can occur in one of these 4 ways: W1, W2, W3, W4. These are the only ways W can occur. Okay, so what I can say, what I said just with plain English, I can express it in the language of events and math notation. W1 or W2 or W3 or W4. Correct? Now, I want you to observe something else, that all of these events, all the W1, W2, W3, W4, are exclusive events. Is that clear? Because if you take any 2, it tells you W1 and W3 require the 6 to be scored at a different roll. The first one requires the roll to be 6, the 6 to be rolled during the first attempt, while the third one, for example, requires the roll to be scored in the third attempt and not in the first. So all of these are exclusive. And therefore the probability of W is the sum of the probabilities of these W1, W2, W3, W4. Is this clear so far? You don't really need to keep notes because you will have this in the MP4 file. You will be able to see that and hear the narration that I'm giving you right now. The only thing that you don't see is my face anyway. I don't think that I'm cute enough You deserve to have my face on the video. Now, what is the probability of W1? 1 over 6, okay? The die has 6 sides. Well, you have one attempt, is 1 over 6. Oops. That was a long 6 here. What is the probability of W2? I hear many answers. Okay, let's see how many, think a little bit, just give it a moment of thought. Number of all outcomes over number of favorable outcomes. You roll twice, and the 6 occurs in your second roll. So what is the total number of outcomes? You roll twice to that. 36, okay? Why is it 36? Because you have 6 outcomes in the first time and 6 in the second. The denominator, therefore, will be 36. Okay, we haven't spoken about the numerator first. Do we agree that all the events, all the simple outcomes for W2, regarding W2, forget the rest of the problem. Just focus now on W2 only. You haven't heard anything else. Just focus on W2. W2 tells you that the total number of simple outcomes related to W2, which means I roll the die twice, is 36. How many are the favorable events? Now we calculate the numerator. You lose in the first time, but you win in the second roll, which means you roll a 6 in the second. How many outcomes? You have 5 because you didn't roll a 6 in the first. So you rolled a number between 1 and 5. And during your second roll, you scored a 6. So that gives you a total of 5 favorable outcomes. Is that correct? Do we all agree? Do you all follow me? Now let's go to W3. What is W3? You roll 3 times and you score the 6 on the third roll. So you fail the first 2 rolls. You don't score a 6 in neither of the first 2 rolls. How many total outcomes do we have here? You roll 3 times. Which is? No, all of them. 6 by 6 by 6, okay? We roll 3 times, so all outcomes is 6 cubed. How many are the favorable outcomes? You roll the 6 the third time. The first 2 times you didn't roll a 6. No. The first roll you have 5 outcomes. In the second roll you have 5 more outcomes. For each selection of the first roll, you have 5 outcomes for the first selection. And I say 5 because you roll during the first and the second roll only between 1 through 5. So you have 5 times 5. The score, the 6 is rolled on the third roll, okay? So you have 5 times 5, so that gives you 5 squared over 6 cubed. And finally, W4, now it's easy to guess the pattern, will be 5 cubed times 6 to the 4th. So the probability of W is 1/6 plus 5 square over 6 cube. Over 6 to the 4. So that's the probability of W. Is it clear? Yes.
Sure, like when you were calculating the altitude and you said schedule
Mm-hmm.
the 5 you roughly because
During the first roll, I didn't score a 6, because that's the description of the event. I scored the 6 in the second roll. So if you try to see pictorially this, and you try to see the square with the 6, so first roll here, second roll here, I need 1, 2, 3, 4, 5, 6. So this is the 36 cube square, the grid here. What are the favorable events? In the second roll, you score a 6. So that allows you, on your first, oops, it deleted it, and your everything to be on the last line, the 6th line, but only these 5. Only these 5. The first one, not the very last one, because the very last one represents a 6 on the first row. So you have only those 5. So the first roll was 1, and the second roll was 6. The first roll was a 2, and the second roll was a 6. The third roll was a 3, and the first roll was a 3, and the second roll was a 6, and 2 more events. Yes?
as far as the number of options on W2, wouldn't it be 30? Because on the first row, you won the first time, you win. But on the second time, if you didn't go first time, you go to the first try, and the second time,
Why 30? No, why 30? You roll twice. The total number of outcomes.
yeah, but the total number of outcomes for W2 wouldn't that be one less because let's say you
No. When we say the total number of outcomes, when I roll twice the die, what is the total number of simple events I have? All the simple events. Which are all the simple events? Any configuration. Okay? It will be 36, yes. That's why I use 36. Ah, I think you're right. And I think I made a mistake. That's a very good point. Can you repeat louder, please? I will repeat it for the microphone because over there I can catch your voice. Stand up so everybody can see you. You're my new celebrity.
on the first roll, if you roll, let's say you roll the 2, you lost the first roll, then you go to the second roll. If you roll the 6 on the first try, there would be no need for you to roll again. So on the second try, there wouldn't be the possibility of having 6 and 3. Like you just saw all
Correct.
you have 1, 2, 3, 4, 5, 6, and then you get the same thing again. Like 1, 1, 1, 1, 2, 3, 4. You wouldn't have the 6 options. You would 1 to go.
No. What underlies here, the problem is conditional probability. I can solve the problem again with conditional probability, but I can solve it with the rules of counting because it's fairly simple, but you got to be careful. That's a very good point. So here's, if I want pictorially to show what he's describing, there's no dispute for the first one, but there will be dispute for all subsequent ones. Okay, now let's look let's look at W2. So pictorially, we have the following picture here. That's very good. One, two, three, 4, 5, and 6. It will be, sorry. So that's the first roll and the second roll. And now we will mark the allowable, the realizable events, okay? And here's on the vertical, we have the second roll. 1, 2, 3, 4, 5, and 6. In the first roll, we say that we can't win in the first roll. Therefore, only 5 events are allowable, not the 6. In my calculation, I said 6 times 6, and I did repeat the same mistake in all the subsequent ones. So I overcounted. I put more. The description of the event says that only 5, 1 through 5, you can score in the first row. So you have only these guys. You can score a 5 and anything else in the second roll. The second roll is open because you're allowed to win in the second roll. So you have, for the first one, so this is 1, 2, 3, 4, and 5. So all the allowable events are those squares that if you add them, there are 5 times 6, there are 30 of them. How many are the favorable events? 5. So we didn't calculate that one. The only mistake we've done was the denominator. Now let's apply the same principle in the calculation of the remaining events. We didn't make any mistake in the calculation of the numerator. Yes? It will all be 1/6. 5 times 5 times 6. And again, the last one will be 5 times 5 times 6. And always we have the same. So all of them will give you 1/6. So all of them will give you finally 4/6. All right? Is that intuitively correct? Yes, it is. Let's look what I had before. Now I will invoke some calculus. Simple calculus. Actually, what did I do? What did I have before? My result before was the wrong result here. Was 1/6 plus 5 over 6 square plus 5 cube over 6 cube. 5 square over 6 cube plus 5 cube over 6 to the 4th. So there is 1/6, a common factor, 1 plus 5 over 6 each time. What is the sum if we continue asymptotically? Well, the sum if we continue asymptotically is 1/6. That's actually that's less than or equal to, because I add an infinite number of terms. I continue playing an infinite number of times. What should be that? 1 minus 1 over 5/6. That gives me again 1/6, so that gives me 1. Okay, so both give me, yeah, it doesn't give me the fallacy I was expecting. This one does the following. What happens here? How many times? I have n times. This is generally, if I roll n times, it is always roll 4 times, and it's 1/6. If we continue a 5th time, what would be again? It would be again another 1/6. So what happens? If you keep playing, eventually you will win, but you can never the probability exceed 1. So in 6 rolls, I would win. But that's not necessarily true. I may never win. I may keep playing forever and ever and ever and ever and never win. So what's the fallacy here? Something's wrong here. Yes?
I'm just really confused. Like, the first time you did it, I understood it. It was like, the 1
Mm-hmm.
6 times, the 5 over 6 times 1 over 6. That makes sense to me. Because, for the first row, it's 5 chances to not get 1.
Mm-hmm.
And the second row, 1 chance to get 6. So if you look at that together, the answer that I understood, but I don't understand why it's really on your 5.
Yeah. And let's go to W2 again. Let's understand that. Yes. No, it's independent. First with second. Uh-huh.
That's good, but what if you wanted to know, what if, let's say that when you roll the die or 6, roll the die, when it goes to 6, it'll explode or something, so you want to know how long it will explode. I would say instead of adding probabilities, I'm thinking
What have we done? So there's obviously one mistake, okay? There's obviously one mistake, because if we keep adding the 6th time, we reach 1. And you know intuitively that this is wrong. The second solution actually is telling you that if you continue asymptotically playing the game, which means forever and ever and ever, the probability of winning is 100%. And you understand that if you keep rolling, spend all of your time rolling a die, at some point, it's very likely, the longer you wait, the more likely it's going to happen. You will roll a 6, and you will win.
Why do those 5s have powers on them?
So somewhere we've made a mistake here. We might have made the mistake not in the counting, but here. We might have made the mistake there. That's another possibility, that we might have made the mistake there. Yes?
Yeah, so it'd be like 1 6.
Essentially is...
Regardless of every time you throw the dice, it's 1 out of 6 chance you get 6.
Yes.
To get yes, it is.
That's just to be true.
All right, so
It
1
is,
out of 6
though.
chance to get a 6, but to get a 6, not the first time, the second time is less than 1 out of 6 chance that you're going to get a 6 on the second roll after not getting a 6 on the first roll.
Mm-hmm. So?
I mean, the die doesn't remember that you didn't score on the first one.
Okay.
So it has to, I think it's just 1 6 or 8.
Do you know what happened here where probably is a mistake? It's that I add events that shouldn't be added together. There is something like I add oranges and then one other type of apples plus strawberries and finally bananas. And the whole thing is bananas. So that I don't keep good accounting here. That's why we get an obvious mistake. Now, it's not that the observation that was made is not correct. And believe me, this is exactly the problem that triggered Chevalier de Marais to prompted actually Chevalier de Marais to talk to Blaise Pascal. Chevalier de Marais believed that it was 4/6. So he couldn't explain the fallacy that if he keeps continuous on the sixth roll, he wouldn't have had a 6. Theoretically, it increases. Why not roll 6 times and score a 6? But he knew that this is not correct. Okay, what happened here is that I created an event to put W in, which is not exactly in the same sample space, because the setting for counting changes. If you see in the first occurrence, the first roll, we have only 6 events, but in the second roll we have 30 events that can occur. So what should have been the proper way is not to add the probabilities, but basically add all the ways this can happen. Do a restructuring under which this can happen. Okay? Or I should have done something else, which basically is more appealing to do when you have conditional probability at hand. So that solution had one very good observation here, W2, a way to find W2, and had a big mistake here, because I added probabilities that do not live in the same sample space. Suppose that we forget that. Okay, let's forget, give me a break. Let's forget my mistake. Huh? I'm allowed to make mistakes.
If you use the sample space of 6 to the 4th and adjusting the probabilities accordingly,
we can adjust them accordingly. Now, if you want to see how many outcomes do we have, if we keep counting, in how many ways how many events do we have? Can we form? How many simple events?
6 to the 4th.
No. Think what he said before. First roll, win at the first roll. 6 events, 6 simple events. Win on the second roll. How many do you have? 30. 5 times 6. Win on the third roll.
25 times 6.
You have 25 times 6. Win on the fourth roll.
125 times 6.
We have 5 cubed, which is 125 times 6. So how many simple outcomes do we have in total? Oh. And then we have to put that. Not win at all, which means how many? Four rolls and all 4 are futile. Five to the 4th. Okay? So these are all the simple events. What?
We're looking for the sample space.
We're looking for the sample space. Total number of simple events. Now, if you add them like that, then that will make more sense. 5 times 6 plus 5 squared times 6 plus 5 cubed times 6 plus 5 to the 4th power. And what is the total number of favorable events? Well, we have 1 for the first roll, 5 if you win on the second, plus 5 squared, which is 25 for the third, plus 125 for the fourth. So that's a better way to count. That's a correct way to count. Now, so that's the probability of W. So what happens is that we don't look at how many events we have for the sample space. Because the sample space win on the first roll, win on the second roll, win on the third roll, win on the fourth roll, or not win at all. That gives you all the possible configurations. Is there any configuration that we have forgotten? No? Then that's the correct result. What is my mistake from the beginning? That solution was wrong from the very beginning. Okay? And that's a good example. And it's a good example to show you that everybody can make a mistake in probability theory. Yes? No, yeah, I was precluding that. I just changed it. That would have been a different game. I changed the game. You stop once, you roll the 6. I think the way you described the game would have been easier. And that line out of the solution that I had would have worked with different numbers. But the way I lined up, I stated the rules of winning the game made the problem very different. So the big problem started from this equation here. That was the wrong equation because the W's were not the correct in the configuration that we're looking at. Essentially, they were not properly calculated. Okay, so that's the.
This stuff that is a failure function or something, 5, 6, like probability of a normal event happening, but event's not happening.
I didn't understand that.
No,
All right. And here is a problem that I have for you. Can you generalize this formula for the probability of W if we have n rolls? So generalize the formula for n rolls. And find the asymptotics. When I say the asymptotics, and find the limit of W as n tends to infinity. And you roll an infinite number of times. What should be that number there? Okay? Theoretically,
1.
that number should be 1. So it's a problem with sequences, a little bit of summation. That's for those who are, calculus die hard. All right? Now, let me move to, that's an optional problem, okay? Let's say this is a bonus problem. How much bonus should I give? What? Me? Give 200 points? No, I may make mistakes, but I'm never that generous. Let's say let's give 10 points. Okay? Let's give 10 points to that bonus problem. Next class, yes. All right? Now, if you have a bonus problem, please work on it on your own. Don't share it with your best friend or your significant other or someone else. It's a bonus, okay? It's for you. You deserve the bonus. Somebody else doesn't deserve the bonus if they can't do it. And yeah, you get it. Bonus points are not mandatory homework. They don't raise the bar. The bar is 300 points. The bonus points are there to help you get a better grade, but they don't raise the bar from the 300. So essentially, no one who doesn't do the bonus problem doesn't lose anything. Those are just for losses down the road. So let's go to conditional probability now. After we got this problem. Yeah, that was very nice. It woke all of us.
So, when you say favorable conditions, is it the same thing as
The favorable simple event, not the favorable conditions. The favorable simple event. When I use the word favorable, the term favorable simple event, I mean an event that fits the description, a simple event that fits the description for which I'm considering. It fits the description, the generic description of the event of whom the probability I'm calculating. It is an event that can occur, yes. At a time, yes. One possible outcome. It has to be one possible outcome. How many of you have done probability theory before? Or finite math? No. Okay, conditional probability. That's nice, and actually it can let us look at this from another viewpoint, the same problem from another viewpoint. So when I use a condition, what is a condition? A condition is basically one extra little piece of information that I know. And if I know that extra little piece of information, then what it does, it reduces the number of simple events I'm considering. For example, suppose that I give you a 4-letter word here. Let's play a game. I give you a 4-letter word, a 4-letter word. Then, if I tell you that the first letter is F, then does this make it any easier?
Yes. A.
You have to guess, let's say you have to guess the word that I have in my mind. No, I'm not saying. Is there a K? No, okay, no. In that word, no, there's no. Okay, let me put it that way, which is again a condition. It's not the F word. Okay, that's a condition. So it removes one word out of the words that start with an F and have 4 letters. That's a condition.
Is there an A?
How many words can we have like this?
Quite a few.
Well, there are quite a few. So, suppose that you have 5 chances to find the word. 6 attempts to find the word.
A.
What is the probability of finding the word? Actually, it's very significant, because once you have 2 letters, or 3 letters perhaps, very quickly you will guess the fourth letter. Because there are rules of grammar that restrict whatever you can put.
For example, one of these.
So who wants to try? First attempt, yes.
A.
Which position?
Second.
No, you can pick in any position, but you have to tell me the letter in which position.
A2.
A into position, no. Another attempt. A D on the last position, no. Yes. N on the third one, no. So now you see the sample space is shrinking. What? E on the third one? No.
And the second one.
What is the second? E on the second one? No. What? No. What should be the proper way to go? Exhaust all. What do you expect on the second word? On the second letter? A vowel, okay? It's more likely to have a vowel. So you exhaust the vowel. What? And actually it's O on the second one. So you have now O on the second one.
Is there an R on the third letter?
We already guessed that.
On the third letter, no. What? There is no O in the third position? No.
Is there an E in the fourth one?
No.
Is there any more vowels?
There are more vowels. That's another.
A in the third one.
A.
A in the
You see, all what you do, what are you trying to do? You're trying to constrict as much as you can the sample space. You're introducing conditions, condition over condition over condition. And all of those conditions, basically, what they do, they just limit your search space. And exactly that's what conditional probability does. Well, I don't want to play the game for too long because we're wasting time. The word I had in my mind is for. Okay, so once I had given you that this is you, then automatically you would have guessed the fourth letter.
Found.
With probability super high.
Found.
All right? Do you see how conditional probability works? And the definition, the mathematical definition, first of all, the notation. A is an event and B is the condition. So I put a vertical line, that's vertical, and B is the condition. So A occurs under condition B. That's my notation. And the probability, what we call conditional probability of A given B, event, is the probability of A intersection B divided by the probability of the condition. Sometimes we call B the a priori condition because it's the given condition. Okay, so all this number here, all that probability is called conditional probability of A. Given B. Is that clear? Okay. Now, this rule has something very, very important. That the probability of A given B is always equal to the conditional probability of A given the condition B times the probability of B. And of course I can reverse that and say that this is also B given A times the probability of A. So conditional probability is a good tool to find the probability of the occurrence, of the simultaneous occurrence of two events. And what I would like to use the word simultaneous with some freedom. Yes.
So, like anytime we have a condition, that will help us to arrive at the probability easy.
Yes, sometimes yes. Yeah. So let's look at the previous situation. Let's apply this to W2 as we had before. What is W2? Lose in the first roll and win in the second. A priori condition.
If we know that we lose in the first roll, then we know then the probability of winning in the second is 1/6. Then I'm supposed to.
I mean, that screen, I don't know if it is. I don't know if the settings are, it seems to be a little bit squeezed. But anyway, the problem is that I have HDMI output, and these are all old analog projectors. So I can use high definition video. I'm sorry. So what is this? Losing the first, winning the second. I would call this one A and this B. And let's apply what we have done before. Look at the end. The end is this thing, the intersection. This is end. How would I write this? This is the probability that A given B times the probability of B. Okay? What is the probability of A given B?
0.6.
I roll a 6 in the second.
1/6.
1/6. What is the probability of B? 5/6. Okay. The mystery arises again. Five over 36, if I'm not wrong. Yeah? 6 times 6 gives 36. Okay? Now, this was exactly the probability of not rolling a 6 in the first roll, but rolling a 6 in the second roll. Why is the probability of rolling a 6 in the second roll 1/6? It's always 1/6. And the result of the first roll and the second roll are independent. So here you have the result of the second roll does not depend on the result of the first roll. That's called independence of events. So here, surprisingly, we calculated in this particular case that A given B is 1/6, which is exactly equal to the probability of A, because A and B are independent events. And what do independent events mean? Exactly this equality. So when we have independent events, A and B are independent events, then the probability of A intersection B, A and B occurring at the same time, is equal to the probability of A times the probability of B. It's exactly a consequence of this rule. So that's a very, very fundamental formula. But this is true only under the independence assumption. Here, when I roll the dice, I have the independence, because the result of the second roll does not at all depend, entirely does not depend on the result of the first, which is exactly what Navia was saying saying before. So the answer would have been 5 over 36. How do we reconcile? Before we said 5 over 30. Now we say 5 over 36. So what's wrong here? Is there any problem? There is no problem. And why there is no problem?
Because we're also accounting what happens when we do roll the 6 on the first roll.
Mm-hmm. Why there is no problem? Because in the previous problem, the correct way to calculate is this, here. And not just sum the events. Okay? So, what was wrong at the very beginning was this summation. This summation was wrong. This was the correct way to calculate the events, and of course that doesn't come into conflict with this particular the way I calculate here the conditional probability. So we have events that do not depend on each other, and those are called independent events. And if the events depend on each other, they are called, when they are not independent, they are called dependent. Okay, now be careful, because this is a typical error. You can use it if you can argue that the events A and B are independent. But if you can argue persuasively that the events A and B are independent, then you can't use it, and you have to go with this one here, which is always correct. So in summary, this requires independence. This is valid always. And that gives us conditional probability. Okay? Now, there are some very important notions of conditional probability that I would like to and we're running out of time, as I see here. So let's work on some problems, and then I will do those things next time, on Tuesday. So the book has some nice problems. I will work on some on the unsolved problems. Take a hand of 13 cards. That's problem number 2. On page 102. So we take a hand of 13 cards out of a deck of cards of 52. Find the probability that at least 3 aces are contained in the card, given that there are at least 2 aces. I'm writing it. There are 2 aces. Find the probability that the hand contains at least 3 aces. Okay, what does at least 3 mean? It can contain how many?
3 or 4.
3 or 4, okay? It can contain more than 4 because the deck has only 4 aces. So the hand contains 4 or the hand contains 3 aces. So if we add the probabilities of these two events, then we have the probability of that we want to find. What is the probability? What do we have here? We have the word given. Given means condition. It's an a priori condition. So you already know that the hand contains 2 aces. So if you say B is the event hand contains 2 aces, given that there are at least 2 aces. Okay, let me solve it with exactly 2 aces, okay? Otherwise, that's your first problem. It will become more complicated. Let's understand with a simple condition. Hand contains exactly 2 aces. So it's a variation of the problem. And then I will show you how it goes with the at least. What you want to calculate is, call this H4 and call this H3. You want to find the probability of H4 union H3 given the condition B. H4 and H3 are exclusive because either you have 3 aces or you have 4 aces. So those are exclusive events, and therefore that results in adding the probabilities. Even if they are conditional, you can still add them. The condition is nothing else but reassignment of the sample space. So all the rules of probability work provided that you keep the condition to be the same on the left and on the right hand side. Right? So what is the probability of the first event? You have 4 aces in the hand given that you already have 2 aces. Let's find in how many ways, let's give it a little bit more breadth. In how many ways can that event occur? Not H4. In how many ways can you have exactly 2 aces in the deck of cards? In the 13th hand. So we have 13 cards out of the 52. In which way can the hand contain exactly 2 aces? We have to, first of all, select the 2 aces to put in the hand. So to select the 4 aces, we select them out of the 2 aces, we select them out of 4. 4 choose 2. It's a combination. Why? Because you select the aces and all the cards for the hand without replacement, and the order is irrelevant. So you have combinations. So now this is the way to select the 2 aces. Now you have 11 more cards to select, which are not aces because we said exactly 2 aces. And now you select the 11 cards out of how many? 48, because you have to preclude the 4 aces. 48 choose 11 for the remaining cards. No, it's 13. 2 plus 11. Yeah, but that's the condition. The condition is I have exactly 2 aces inside the deck of cards. Now, what is the way that the hand contains exactly 4 aces? 4 aces. That's event H4. Now you are calculating the number of the favorable ways this event can occur. So the 4 aces are all inside the deck of cards, which has 13 cards. What is the how many ways can you choose the remaining 9 cards? Out of the 48, correct? So it's 48, choose 9 for the first. What would be the second one? 4 choose 2, 48 choose 11. What would be the probability for the ways that you choose H3? Exactly 3 aces. That would be 4 choose 3 to select the 3 aces. And now you select the remaining 10 cards out of 48 cards. 48 choose 10. You add the 2, as you see, you have a common denominator. That gives you the probability that you have at least 3 aces in a deck of cards, given that you have exactly 2 aces. All right? Well, we'll stop here, and I will continue the recording to mention the other. Okay, I'm going to go back after all the files that we have done to say a few things about the problem we solved here. There are actually several aspects that that I kind of lost during the initial presentation in the class. We have a game. Let's repeat the problem. We have a game with a die. We roll the die. The die has 6 sides, and we can roll the die up to 4 times. And the winning rule is that if even through the 4th roll you score a 6, then you're a winner. Otherwise, you're not a winner. Obviously, if in the first roll you roll a 6, you're not going to roll 4 times, 2, 3, and 4. The game stops and you're a winner. Therefore, as we mentioned at the beginning, indeed we have the winning event, W, splits in 4 different sub-events. W1, W2, W3, and W4, as we explained in the class. And W can occur under all of those events. Now, the truth is that this equation here is correct, and I'm going to rewrite it again, but I will review a little bit the computations. So P of W, the probability of W, is the sum of the probabilities of these other events, W3, W2, and W4. And actually, if we want to see these events, then here is the best way to understand it. Let me review a few things. And let's rewrite. Let's write, because otherwise it will not become very clear. So now we have a clean screen. Clearly, that is the correct answer for W1. Now, what is W2? Let's analyze what is W2. We say it here. Not score a 6 during the first roll, but score a 6 during the second. That comma here is essentially but or and. So let's write P of W2 is the probability of not rolling a 6 during the first time and roll a 6 in the second roll. Notice at the end that we have here. And I will use the conditional probability that we spoke about it later to calculate the probability of this event. So this is the probability that you roll a 6 during the second roll, given that you rolled no 6 in first roll, times the probability that you roll a 6 in the first roll, which is that you roll no 6 in first roll. That probability is equal, the first one, all of this thing is equal to 1/6. And this probability here is equal to 5/6. So overall we have 5/36. And this is the correct answer. Now, why the first probability is 1/6? Rolls are independent events. Therefore, the probability of rolling a 6 in the second roll, given that rolled no 6 in first roll, what happened in the first roll and what happens in the second roll are completely independent events. So this is equal again to the probability of rolling a 6 in the second roll or in any other roll, and this is always equal to 1/6. That's why I have here 1/6. Likewise, the probability of W2, W3 is equal to the probability of rolling a 6 in the third roll, given that rolled no 6 in previous rolls, in all previous rolls. And of course, what you roll in each roll, times the probability that rolled no 6 in first and second rolls. So this will give us, actually I have an easier way to do this. And essentially it's the same, but it's less writing. So let me do the easier way. This is the event. Roll 6 in third roll and roll no 6 in first and no 6 in second roll. And as we mentioned, what happens in each roll is independent of what happens in any other roll. So this, and the last event here, that one, are all independent events. And since those events are connected with and, the respective probabilities, the probability of the intersection of all of these things occurring together jointly is equal to the product of the probabilities of the respective events. And again, what causes this is independence. Let me squeeze it here. So that would be equal to roll 6 in the third roll, times the probability of roll no 6 in the second, and times the probability of roll no 6 in the first. And clearly these probabilities here are equal to 1/6 times 5/6 times 5/6, and this was given as 5 squared over 6 cubed. And likewise, P of W4 is equal to 5 cubed over 6 to the 4th. And very correctly, as I initially solved the problem, the probability, I want to keep that part here for our discussion. So the probability of W is 1/6 plus 5 over 36 plus 5 squared over 6 cubed plus 5 cubed over 6 to the 4th. That's the correct answer to this problem. Now we went here and we try to solve the problem with counting. And clearly what I said here, this is wrong. And I will justify why this is wrong. So even if we generalize the problem, the formula is not going to give you the right answer. However, I'm keeping the bonus. I'm not destroying the bonus. But let me remove it from here because I need space. If you want to understand what is going on, let's see what we did here, which sparked a very vivid discussion in the class, despite the magic weather. That was very conducive for a late afternoon nap. Here we count the cases under which the second event W2 can occur. And we said that all cases are 30. Because we have 5 times 6. These are all simple events. All simple events where in the first roll we roll 1 to 5, and in the second roll we can roll, since we can win in the second, we plan to win in the second roll, we say we win in the second roll, we roll everything, 1 to 6. So these are all simple events, and in class we mentioned that the favorable simple events, so the number of the favorable simple events, which describe how we win, is all numbers 1 through 5 for the first roll and 6 for the second. So we have only 5 of them. And then we made the probability, we calculated with this the probability to be 5 over 30, and if you make the simplification, this is 1/6. However, when we calculated the probability here, we found 5 over 36. So what is correct? 5 over 30 or 5 over 36? And the answer is that the correct calculation, if we're to stop to go only up to 2 rolls, is not 5 over 30 for W2, but it's 5 over 36. This is the probability that we will end, we roll a 6 in the second roll, and we didn't roll a 6 in the first. Why do then we have a discrepancy? What's wrong? Is the theory wrong? The rules of counting, that's where exactly the error occurred, and that's where exactly I missed it in the class, and that's why this formula is wrong. The rules of counting for calculating probabilities are only valid if all simple events are equally likely. Well, here we have a case where all simple events are not equally likely. And let me just put that further down so I get some free space and explain. So here we'll continue with the die problem, the Chevalier-Desmarais problem. We have the following pathology here. When we say for the calculation of W2, roll a 6 in the second and roll 1 through 5 in first. We have one situation here. We proceed to the second roll only if in the first roll we roll between 1 and 6. So the chain of the events does not lead exactly to simple events that all share the same amount of probability. Clearly, we have 30 simple events. But the first 6 events, the events of the first roll carry a bigger weight. And that weight can only be realized if we use the conditional probability. That's why the probability of W2 ends up being 5 over 36 instead of being 5 over 30. Because although we have the same number of simple events, the simple events, the 30 simple events do not all share the same amount of conditional, the same amount of probability. And therefore, if we try to just count simple events under which W2 can occur, favorable over all simple events, we end up with the wrong answer. This is exactly why the equal distribution model does not work. The equal probability model does not work. And this is a case where exactly it does not work because what it does not understand, the way we constructed the model, it does not understand the rules of independence between the rolls. So that being said, you would ask me, Where should I apply one and where should I apply the other? And I would say the answer is not very simple. And I wouldn't like to elaborate more in that regard because that is a problem that doesn't really concerns us a lot, at least in the context of probability for statistics for the sciences. That's something that relates to more to deeper question, the deeper to somebody who would like to learn probability theory at a deeper level. And for this reason, I wouldn't like to go any further. So the correct answer is this, as we did it here. That's the correct. And this clearly, which was derived by putting all simple events together and assigning to them the same probability, is wrong. So just eliminate this. And I guess with this, I would like to just make one more remark and finish. What is the remark I want to make? Suppose that we keep playing, we keep rolling. As you have noticed, if we roll on the fourth time, if we need to roll for the fourth time and we win, we score a 6 on the fourth roll, the chances for this occurring are 5 cubed over 6 to the fourth. And in general, if we continue, we roll n times, and the nth time we stop because a 6 is rolled. No 6 has been rolled in the previous n minus 1 time. The probability of the occurrence of this event, I would call it W sub n, is 5 to the n minus 1 over 6 to the n. And here I would ask the following question. What is the probability that of winning if we play n times? If we have to roll n times. Clearly, that's the sum up to n minus 1. And you can verify this formula if you plug n to be equal to 4. You will see that you have the formula derived before. And of course that one is 1 over 6 to the sum of the geometric series. Five-sixths to the kth power. And if you look a little bit at on your calculus 2 books, This is equal to 1 over 6 times 1 minus 5/6 to the n power over 1 minus 5/6. This will cancel this, and we have 1 minus 5/6 to the n power. And as you see, this goes to 0 as n goes to infinity. Which says that if we keep rolling, the obvious will happen. At some point, we will score a 6 if we spend all of our life just rolling the die. At some point, merciful Lord will give us a break. We will see this example sometime later, the so-called geometric distribution, because this is where thunder lies. But what is the moral of the story from my mistake in class and what we just now discussed is that be very careful when we have conditional probability. Sometimes the equal assignment, the model of equal probability assigned to all simple events may not be the correct model. And this is exactly one of these particular cases. With this, I'm going to close the recording and wish you a great day.